So, dear colleagues, it's 4:30 in Moscow, and I believe we could start the second day of our conference. So it's great pleasure to start this day, because actually this conference is unique for us because it's first transatlantic conference, and we have participants from Russia, Canada, United States, and Brazil at same time. So thank you for all participants, for all who connect us via online, all online possibilities. And our first talk for today is a lecture presented by Alexey Polotsky from our Institute of Macromolecular Compounds. And his talk will be, I think, closely connected with the lecture of Sergei Sheiko that was yesterday. So, Alexey,
yes, to a very certain extent.
Talk to you.
So, dear Sergei, dear colleagues, it's my great pleasure to be here and present the results of our talk. So today I'm going to talk about unfolding of globular polymers formed by linear and branched polymers. So these recent advances in experimental techniques have made it possible to operate single molecules and macromolecules and probe their mechanical properties using such instruments as atomic force microscope, optical, or magnetic tweezers. So these tools became some kind of standard in modern polymer physics and molecular biology. So it is some kind of standard tool when one wants to get an insight not only into mechanical properties of these macromolecules or complexes, but also to internal structure of the proteins, molecular motors, etc. Today I'm going to talk about. Thank you. Today I'm going to talk about mechanical unfolding of macromolecules of globules made by macromolecules of three types. We start with the simplest case of a homopolymer globule formed by a linear chain macromolecule, and then we pass to a more complex branched architecture and first consider a homopolymer globule formed by comb-like macromolecule where side chain and main chain have the same chemical nature. And finally, we discuss the unfolding of comb-like copolymers formed by amphiphilic comb-like copolymers with solvophobic side chains and solvophilic main chains. So in a selective solvent, such comb-like copolymer forms a unimolecular micelle. So we start with a stretching of a homopolymer globule formed by a linear chain. So this is a very nice system for theories because it is characterized by only two parameters, the chain length or the polymerization degree and the solvent quality. So we study stretching of this macromolecule in the so-called position clamp mode, where one imposes the distance between the chain ends and measures the force with which the macromolecule reacts to such deformation. Our main tool for solving this problem and all the others I will discuss today is the Schouten-Flier numerical self-consistent field approach. It is based on the solution of the self-consistent field equations on a regular lattice, and the symmetry and the type of the lattice is determined by the symmetry of the problem. For the problem of mechanical unfolding of globular polymers, the symmetry is obvious cylindrical, so we solve this problem, solve the self-consistent field equations on the cylindrical lattice where there are two gradients in radial and the axial direction. So the solution of the self-consistent field equation give us the density, the equilibrium density distribution in our system, and the free energy. Differentiation of the free energy with respect to the distance between the chain ends gives us the reaction force. So we did our calculations using the SF-box program developed by our colleagues in Wageningen University in the Netherlands. So this is a typical examples of the force extension curves of global unfolding, where we see that on this curve there are three distinct deformation regimes. So at small deformation, we observe a strong increase of the reaction force with extension. Then, after reaching a peak, we see some kind of plateau, or more exactly the quasi-plateau, where the reaction force slightly decreases as we increase the distance between the chain ends. So, in other words, the system in this regime exhibits a negative extensibility. The larger it is extended, the smaller is the reaction resistance to the deformations. This quasi-plateau regime exists in a quite wide range of deformation, and this range increases as we deteriorate the solvent quality, and then after reaching some certain point, the force drops down, and then starts to grow again. And you see that this growth fall into a universal curve. In order to relate these deformation regimes to conformational changes in our macromolecule, let us consider in more detail the evolution of the density profile. So a small deformation, the globule changes its shape from spherical to extended ellipsoidal one. Then at some point, the ellipsoidal structure becomes unstable and the globule splits into two parts. Here we have again a globular part which coexists with the extended chain. So it forms a tail, and the globule forms a head, and therefore such a structure is called a tadpole. As the distance between the chain ends increases more and more, the size of the tail increases, the number of monomer units and the size of the head decreases. But what is interesting, at the same time, the average polymer density in the head doesn't change with the extension. And then after reaching some certain point, the head disappears, and what we have is the uniformly stretched open chain. So the globule unfolds completely, and this corresponds to the third regime on the force extension curve. We could also construct the diagram of states of extended globule, so where we plotted the points of globule tadpole and tadpole transitions as a function of the chain length n. So we see that with increasing chain length, the width of this area, which corresponds to the microphase segregated tadpole regime, increases. As we decrease the chain length, these two transition lines come closer to each other and then merge at certain point, which is nothing but a critical point for our system. And if we take a chain shorter than the critical length, its deformation behavior will be different that we have seen before. Here is an example. So if we take the globule below the transition point, we see that its extension doesn't lead to microphase segregation. It just leads to deformation of the globule shape as a whole, from spherical to prolate, and as the shape changes, the polymer density within the globule decreases. So again, below the critical point, we observe a very different deformation behavior. So now let us move to the second part of my talk and consider globules formed by macromolecules of more complex architecture, namely we consider comb-like homopolymer where the main chain is decorated by side chains grafted onto the main chain at regular intervals. Both the main and the side chains are made of the same monomer units and being put into a poor solvent under poor solvent conditions. This macromolecule collapses and forms a globule. And we study its mechanical unfolding by imposing the distance between the ends of the main chain. So if you have a look at the force extension curve, we will see that if the short chains are densely grafted to the main chain, the picture qualitatively is very similar to what we've seen for globule made of linear chains, so 3 deformation regime, including this smooth quasi-plateau in the middle. But as we decrease the grafting density, increase the distance between grafted chains, the picture changes. So we see that the quasi-plateau regimes, in the quasi-plateau regimes, oscillations occur, and as the amplitude of these oscillations decrease as we increase the extension, the distance between the ends of the main chain, and we also see that in a poorer solvent, these sawtooth non-monotonicity are more expressed. They become even more expressed if we increase the length of the side chains. At the same time, if we then even more increase the distance between neighboring side chains, we will see that the wavelength on this sawtooth becomes larger. Correspondingly, this is because by decreasing the grafting density, the number of side chains decreases, and as a result, the number of teeth on this in this regime decreases too. So, to what conformational changes this sawtooth pattern corresponds? So now we consider again the evolution of the density profile. Here we consider integrate. Here we decided for the sake of better visualization to integrate the two-dimensional different profile with respect to radial coordinates. We have this results in these profiles of the monomer units distribution along the z-axis, along the axis of extension. So we see that at small deformations we have a single globule. Then, starting from a certain deformation, 2 short linear tails appear at the end of the globule. But then you will see that a second very small maximum appears on the right side of the big globule. This means that as we increase the extension more and more, so the number of these small peaks increase, and actually each this small peak corresponds to a small globule formed on a tail of a tadpole structure. But then, when we reach some certain extension, the big globule disappear, and we obtain a necklace-like structure where with a small globules sitting on the main chain. So, in terms of this profile, this corresponds to this very nice sinusoidal pattern. So, These pictures can be summarized in the following simple picture describing the scenario. So at weak deformations we have an ellipsoidal globule. Then we enter the tadpole regime where on the tadpole's tail small globules sit, and when the big head disappears, we obtain a necklace-like structure with small globules sitting on the sitting on the tail. So finally, let us discuss the third system, where we again consider complex copolymer, but in this case, the chemical nature of main and side chains is different. So main chain is solvophilic, is soluble in the solvent, while the side chains are considered to be solvophobic. Under this condition, this macromolecule can form a unimolecular micelle. It contains a dense globular core formed by side chains, which is decorated by a corona formed by main chain spacers. Again, we study the extension of this macromolecule, this unimolecular micelle, by imposing the distance between the main chain ends. Here are examples of the force extension curve for a certain set of architectural parameters upon variation of the solvent quality for the side chains. And we see that, similar to the previous case, a sawtooth pattern develops in the tadpole regime. This corresponds to these conformational changes in the chain. Again, first, the micellar core is deformed as a whole. Then, at certain extension, we see that a small cluster containing 4 side chains appear. And as we decrease the distance between the main chain ends more and more, the next clusters appear, and its aggregation number, the number of side chains in each cluster increases and decreases. So I will discuss this issue below. Finally, we come to the point where the big micelle disappear and all side chains get distributed between several clusters, and with the following increase in the extension, we see that the number of small clusters increases, and the aggregation number of each small cluster decreases. So this plot illustrates the change in the number of clusters in deformed complex macromolecule. And here we also had an opportunity to compare our self-consistent field results with the results of the Brownian dynamic simulation made by our colleague Ivan Mikhailov for similar set of parameters. And what's quite surprising for us is that we see not only a qualitative but a very good quantitative agreement, despite the fact that Brownian dynamic simulations were made in continuum, while self-consistent field calculation, as I said, explore lattice model. So we see that nice Brownian dynamic snapshots of the deformation of the micelle as a whole, appearance of the first cluster, the following cluster, and disappearance of the big head. So in full accordance with our self-consistent field result. So these plots illustrate conformational changes in deformed micelles, namely the number of side chains in a big head and number of side chains in one small cluster. So we see that in the first regime there is only a big head and no small cluster, then a first small cluster forms. It already has an aggregation number about 4 or 5, and with a following increase in the distance between the chain ends, the aggregation number of the cluster continuously increases, and the number of side chains in the globular head continuously decreases, which means that upon extension, side chains continuously, one by one, leave the big head and join the small cluster. But at some point, the system decides, so to say, to form the second cluster and redistribute the material between two clusters, and this is accompanied by the jump in the average coordination number, aggregation number per cluster, and a small jump in the number of side chains in globular head. So this process is repeated several times up to the point where a big cluster disappears and all the clusters have similar size. And then, yes, you see there is no more head anymore, and the average number of side chains in small cluster progressively decreases as the number of cluster increases in the system. So, then we can finally relate these conformational changes to the force extension curve. So again, first regime corresponds to the growth in the force. Then we have this sawtooth pattern, and each drop in the reaction force corresponds to release of a next new cluster. And in the last regime, there is the reaction force grows on average, but there are some small jumps down, which corresponds to formation of small clusters to increase to the number of clusters on the main chain. So we were also able to develop a simple theory. In order to do so, we consider all possible states of stretched macromolecule, stretched micelle, tadpoles with big head and small globules on the side chains, but also we have considered alternative structure where the micelle is divided by clusters of equal size. Using this approach, we could calculate a force extension curve as well, and you see that at least qualitative, the agreement between our SCF results and the theory is very good, despite the fact that the theory was really based on very rough model and simple and strong approximation. And yeah, in framework of the theory, we can also calculate other characteristics, and I just say that these curves are qualitatively very similar to those curves which are shown before, which were observed by self-consistent field calculations, Brownian dynamics simulation. Then I come to my conclusion. So I have shown you that, in principle, mechanical unfolding of collapsed macromolecules of linear and branched architecture typically occurs in 3 stages, and one of the most fascinating stages is formation of microphase segregated state, where a globule coexists with the extended part. So for linear homopolymer, the tadpole's tail is a simple stretched linear chain, but for collapsed like copolymers, it has a more complicated structure, so of a necklace of small globules or clusters sitting on the tail. And this complicated structure of the tail is reflected in the non-trivial sawtooth pattern on the force extension curve. For those of you who want to know more about the last part of our study, I invite to visit the poster session which is organized online on the conference site, and see this poster by Anna Ivanova. And my thanks to Dmitry, who arranged this poster section, in my opinion, very, very, very well. So I would like to thank the co-authors of my talk, Professor Bernstein, Professor Borisov, and Anna Ivanova. And Anna, by the way, is also the person who prepared the abstract book of the conference, and I also appreciate her work very, very much. I also thank Professor Leemakers, who provided us a program for making self-consistent field calculations, and my thanks to Ivan, who did Brownian dynamic stimulation in the third part of our work. So thank you very much for your attention. I am ready to answer your questions.
Okay, thank you, Alexei. I think we have time for a couple of questions. Any questions here? No, maybe some questions in Zoom?
Yep, I have a question.
Yes, Mika.
So for this force extension curve, so I think in real units we typically in piconewton forces, right?
Mika, I'm sorry. Could you repeat your question?
Oh. Okay, so if I look at the real system for the force extension curve, so we are talking about forces in the piconewton range. Am I correct?
Yes, actually, if you look at the force extension curve for, say, proteins, you will have quite complicated structure with many peaks. So each peak actually would correspond to unfolding of a certain element of the tertiary structure of the protein, or tertiary or secondary structure of the protein.
Yeah, that was exactly where I was heading with this. So if I look at the protein, if I have something that's intrinsically disordered protein, so something that doesn't fold to a nice structure, so what would one expect to see in such a case? Because I would imagine there'd be lots of fluctuations. Maybe some of those sawtooth patterns might exist, but I would imagine them to be a little bit less pronounced, if anything.
Oh yes, you are completely right. If you look to experimental force extension curve, or even to the force extension curve obtained by molecular dynamic simulation, they of course rather noisy, and one have to invent some trick with averaging and extracting information about it. Yeah. This picture is certain correspond to equilibrium state, and therefore it's very smooth and very nice. In real systems, yeah, the picture is even more is noisy. Did I understand your question correct?
Yeah, thank you.
Okay, so thank you, Dmitry.
I have one little question about previous talk of Stanischko and his systems. As I understand, the polymers is like the same, the side chains and polymers, and they measure mechanical properties. And my question is this so like behavior of mechanical properties will be seen in some gels or such? Can be seen.
I think yes. If you include this kind of macromolecules into a network, you might see this non-trivial behavior. But the point is that the spacers between branching point in the network should be quite long. So the network must be quite sparse. But if you are able to make such a network, yes, I think that such an effects will be present in the system.
Yeah. So thank you, Alexei, once again. And So our next talk will be online, and the lecture will be given Maria Samalkorpi from Finland. It's School of Chemical Engineering in Aalto University. So Maria, are you here? Do you hear us?
Yes, I can hear you. I hope that you can hear me as well.
Hello. Yeah, everything very nice.
Yeah.
So talk of Maria will be about understanding biomacromolecular materials via computational modeling that connected with all things that we do in our group and in our several laboratories in our institute. So Maria, time is yours.
Okay, so before I start, I'm checking that my voice is okay. So,
yeah,
okay.
Loud and clear.
Great. Okay, so first of all, thank you very much for this invitation. I'm delighted again to speak at the institute in St. Petersburg, even though this time I couldn't come there physically present. So I have today a little bit different topic from last time. I'm going to be talking about biomacromolecular materials, and in particular protein materials, and how to do biosynthetic silk-like modular protein constructs via computational modeling. Okay. So first of all, examples of structural protein materials in nature. These include quite a bit of familiar materials. Here, nacre, so that's the shiny substance inside a seashell. Then another example of structural protein material is muscle feed adhesive proteins. So the proteins that glue the muscles to surfaces. Additionally, spider silk, so spider webs, they are also structural protein materials that self-assemble. And another example, sandcastle worm proteins, so the adhesives that these fancy worms use to build their beautiful sandcastles, they are protein materials. And then from maybe medicinal point of view, protein amyloids are also structural protein materials. My talk today is going to center around this type of materials and understanding them, going towards design biosynthetically to build them. Okay. The common thing for all these structural materials that I showed as example is that they have a pre-assembly step called liquid-liquid phase separation of the proteins in them. And that has been demonstrated for all these examples that I showed on the previous slide. So the liquid-liquid phase separation, it as a phenomenon, it refers to soluble proteins that spontaneously self-assemble in solution such way that they start forming condensated droplets. So droplets that are rich in the protein, surrounded by a liquid phase where there is much less of the protein. So there is spontaneous liquid-liquid phase separation of the protein solution into protein-rich domains, protein-dilute domains. This is what it looks for our example protein, the silk-like protein that I'm mostly going to be talking about today. So those little spheres that you see on the optical microscopy image, those are the protein condensates, and then they are surrounded by the dilute phase. These references below here, they are the condensate formation as a pre-assembly step for the aforementioned materials that are there experimentally. Okay, a little bit of background for the liquid-liquid phase separation. I think many of you may have heard about this in context of intracellular and biological functions. So it's crucial for inter and intracellular biological functions. That is not our interest in this topic. We focus on this phase separation phenomenon as protein materials pre-assembly step. So then taking that into account, the requirements for the liquid-liquid phase separation are that these proteins need to be soluble, but then to form the condensates, they also need to have attractive regions. So there needs to be enough attraction between the soluble proteins that they actually like to form the condensated droplets. Yet that attraction needs to be so weak that also the condensate phase remains liquid and that some of the proteins remain soluble. In practice, what this means is that at least part of these phase separating proteins have a high conformational flexibility, so they have intrinsically disordered regions typically in them. Then to control the phase separation response, one can use the protein species, so what protein it is, ionic strength, pH, concentration, temperature. There is quite a variety of things that control whether it mixes, so forms the one-phase region, or whether the two-phase spontaneous phase separation occurs. So the basic things about this phase separation are pretty much known. There is quite a few reviews about it available. There are more than those 4 that I listed, but just provide an idea. This is a well-known phenomena fundamentally. What is less well known, how can one really use this for design of materials? So the research target that I'm talking about, it's about biosynthetic protein materials design so that we could get materials with desired properties via this liquid-liquid phase separation. And what I'm targeting here is access by designed block constructs, so that we have proteins that one can choose what blocks one can put into them and then get desired materials properties via that. And as an intermediate step, I'm also going to be talking about controlling this phase separation response to get the materials out. I'm going to be showing quite a bit of experimental data. The data that I'm showing that is experimental, it's all from Markus Linder's group. He's also working at Aalto University, Finland, and he's a key collaborator in this project. He's the one who is realizing these proteins biosynthetically and doing these block constructs. I'm a computationalist. I'm going to be talking about computational approaches, so please bear with me if I can't answer your experimental or questions about the experimental things. I may know some things, but I'm really the computationalist in this topic. Okay. So the protein chosen for the study, it's a silk-like modular tri-block protein construct. And by tri-block protein, I mean that the protein has 3 parts, so 1, 2, 3. And in this case, it's exactly as drawn here in this cartoon. So there are like lump-like end units that have crystalline structure, well-defined ordered structure. And those end units, the terminal domains, they are cellulose binding modules. I believe quite a few of you are also working on CBMs. So this is a familiar common protein. It's binding with cellulose readily, and it's easy to work with because it attaches quite nicely to other proteins. The middle part here, it's flexible. It's intrinsically disordered. It's called AQ, and it's actually a repeating sequence of these AQ units. It resembles spider silk protein from the common European garden spider, the Araneus diadematus. It's not exactly the same, it's just resembling that one. So it's almost the same as the garden spider protein. Here is a sequence of this protein. So it has CBM at the end. Then there is a linker to connect it. This is just a technical point. And then there is many repeats of the AQ units. Again, at the other end, linker, CBM, and the histidine tag that's needed for purification. The properties of this protein, why we chose it. So for the modeling, we chose it clearly because there is a lot of experimental work close by on it. And it's known to do this LLPS. It's known that this LLPS is prerequisite for it forming nice protein fibers. It's also very well characterized for adhesives. So this sandcastle worm-like response of protein materials. And then we know how it's this liquid-liquid phase separation behaves to salt and pH. So there is quite a bit of experimental knowledge already on it before we started modeling. Okay, so starting point for the modeling. This is an image of, or a cryo-TEM high-resolution image of this fiber-forming silk-like protein condensate. So this is the condensate droplet imaged by cryo-TEM. If one analyzes the pore sizes there, so it's forming a porous structure that has bigger pores, smaller pores, and it looks like a sponge. The pore sizes there, they have a quite well-defined distribution. And looking at that pore size distribution and considering the protein that is being used to create this condensate, it's quite curious that the protein extended. It's a little bit over halfway what is the characteristic size of those pores. So that actually means that these pores are occurring at the single molecule level. When we realized that experimentally, it occurred that it would be a rather good idea to start modeling this. Like, what is really happening there? Why is the condensate structure that? How are the fibers forming from this kind of material? How do we get biosynthetic silk out of this material from molecular level? So as already said, the cryo-TEM is showing biocontinuous assembly structure, and then that the pore diameter is proportional to the protein length in the experimental system. And the research question that I started answering on this field was that can molecular modeling actually reveal assembly mechanism there and then the fiber formation control factors? So we started modeling this via all atom molecular dynamic simulations and on a related protein construct. So on this CBM AQ3 CBM silk-like protein in solution. And what you should notice here, the simulations are employing AQ3 and the experiments are doing AQ12. So there is more AQ blocks in the experiments than in the simulations. This is just merely from the simulation point of view becoming unfeasible if the protein is very long. Methodology is listed here. In simple terms, these are CHROMAC simulations, atomistic detail molecular dynamic simulations, and we are matching with the experimental protein concentration, which is 200 milligrams per milliliter in that cryo-TEM image, also in the microscopy image that you saw, and in some other data that you are going to see later on. Individual simulations are 200 to 300 nanoseconds, which is not a huge amount for intrinsically disordered proteins. I'm going to comment on that later. And we are doing both individual proteins and then we are constructing multi-protein constructs based on those. The initial configurations are quite extended so that they can really fold to whatever they would want to fold, but they do not reach equilibrium in that 200 nanoseconds or 300 nanoseconds. This, let me try to get the video on. Okay, so this is what the simulation looks like for one single protein. So first it is pretty extended and it falls onto a compactified structure where alpha helices are coming together and then also the CBM end units are coming together. Okay. Then if I start analyzing how do these structures look in solution. There are two families. In one, the proteins are extended, but the middle parts are together here. And then other family where also the CBMs are together. So essentially the radius of gyration, it falls into two sets in those intrinsically disordered segments. And also the fraction of alpha helices, let me get the laser pointer again, it's varying depending on what the family there is. The alpha helices form sticker-like contacts and compactified structures, and then they differ by how the terminal unit interactions are. I can analyze this further. So this is pretty much consistent with what I just said. So here is a representative conformation of those folded structures. The beta sheet in the terminal units is showing us that crisscross pattern, and then going forward in analyzing what kind of contacts there are, the middle region alpha helices and the short beta strands, they form sticker-like contacts both with the beta sheet ends and with themselves. Okay, so that's the thing that's compactifying the protein. Then putting 10 of these in one simulation box. So this is a much bigger simulation. The box is around 16 nanometers now. What we are getting out, we are getting porous assembly structure. And same way as before, we can analyze what kind of contacts there are. The contacts are pretty identical as in the single protein case, but now between the individual or the different proteins in the solution. So we get similar sticker-mediated contacts as for individual proteins. We get terminal unit contacts that form a spanning network in the simulation box, and those are bearing load. And as I already said, this is quite incomplete relaxation, so we needed to run lots of these simulations. So starting from different configurations, starting from different protein structures that are being put in. So then how does this look in practice? So this is how the protein network evolves in a molecular dynamic simulation in atomistic timescale. And what you probably see from here, the end units are pretty attached. They are tightly holding together. And then the alpha helical parts, they are more flexible. They are the ones that are causing that fluctuation there. And no, it's not fully reorganizing during the simulation timescale. Then going back to the actual experimental finding, this was the finding, so porous structure and pore size approximately the protein diameter. We did even more large systems, so 28 proteins, 200 milligram per milliliter concentration, and analyzed this one for similarity with the experimental structure. And what is coming out there is that we get pore size that's shifted to smaller scale than what the experimental size is, but remembering that the experimental protein is 12 units and the simulational is only 3 units middle part, it's matching pretty consistently the structure that one could envision from the cryo-TEM. So the conclusion here is that the terminal unit CBMs are bearing the load. They form a spanning bicontinuous network for this condensate structure. And to show that one, like how do the end unit contacts or the alpha helical clusters show in this big simulation system, there are a couple of examples there. What we run into here is that there are stronger sticker contacts between the end units, then there are weaker sticker contacts, and the crucial thing here is that we run into timescale issues with the relaxation of the system and the dynamics of the system. Before going to how we resolve that, I'm now going to show how fibers are pulled from this condensate, and then how that protein simulation result, how it kind of can be translated into how the fibers are being formed from the condensate. So when one is pulling the fiber, the end units hold on. It's the middle part that unzips, and that enables pulling the fiber, like it unzips step by step. So this actually relates with the previous talk that we just heard. It has weaker contacts that give way first, and then the stronger ones hold on and carry the fiber formation. Okay. Then I said that we run into problems with the timescales. We turned into very coarse-grained simulations. So the thing that I'm showing next, it's Brownian dynamics and coarse-grained modeling approach toward rational design of these triple proteins. So we realized very fast that in atomistic scale, we cannot get to dynamics of the condensates. We cannot get their dependencies on really or the equilibrium structures at material scale that would come out of there. So what I have here, it's the atomistic structure from the simulations that I shall show, and then I'm coarse graining it. So I'm taking the end units and making them into big blobs. Then I'm looking at what else is there. I'm taking the stickers that were the alpha helices and the beta sheets in the flexible part. And this is intrinsically disordered. They are not always at the same place. There are sequences there that are more prone to alpha helix formation. I don't really know where they exactly are. I know the likelihoods of them, where they are going to show up and how many there are approximately. I turn it into a triblock construct that has end units, bigger ones, and then stickers in the middle chain. And I'm not really going to think about how many of those middle parts there should be. These simulations that we see have 7 in one silk-like protein unit. So 7 middle blocks and 2 end units at each end. Okay. So then we have this kind of bead model with coarse grains beads approximately matching the atomistic construct. Then we do Brownian dynamics. So for those of you who are not familiar with Brownian dynamics, the method contains a friction term that's proportional to what is happening to the particle motion. Then there is a stochastic term, and then the interactions of the molecules in the system or the beads in the system, they are captured by an external interaction potential. So crucial for this system, we need to have the interactions between the beads. And those are described by Lennard-Jones bead-bead attraction. So this is a simple Lennard-Jones bead model. And then to hold this protein together, we put Feeney bonds between the neighboring beads in the chain. The coarse-grained parameters, they are based approximately on the atomistic detail modeling results. So we get bead-bead attraction is dominated by the end units. So for the end unit beads, the attraction is much stronger than for the middle beads. And then the Feeney parameters are approximately what would give the conformations of the atomistic proteins. Okay. Then what can we do with this model? Experimental data on varying the silk-like protein length. And in practice, what is being done in experiments, there is one of these silk proteins, but it's connected to another one so that there is actually repeating those end unit beads also in the middle by the way that it's constructed into repeating length units. And experimentally, we know that the condensate structure is quite dependent on how long the silk-like protein is. So is it 1 repeat, 2, or 3? It's also affecting quite a bit on the dynamics, so diffusion coefficient of the proteins, and also how those droplets are coalescing. That data I'm not showing here, but the viscosity of the solution is also dependent on the chain length. So we used the Brownian dynamics model for this computationally, and the assembly structures are here. What you should be seeing there is that the assembly structure is actually changing quite a bit due to the difference in the ratio of the A and B beads. So for the short one, it forms uniform domains that are connected, and going longer, it's not any more connected in terms of end unit beads. It's more kind of fractionated. And this is also affecting, or this can be seen also in the conformations of the proteins. So what we have there are pairwise connections in different amounts between those strongly attractive end units, depending on the chain length. And that changes the conformations. So the proportion of extended proteins changes. And these are, of course, they are connected to their neighbors. So this is not the whole story. It also within those condensates, the diffusion is changing. So we actually get to the dynamics response via the Brownian dynamics model, and it comes via the change in the assembly structure. So dynamics changes, nature of the mechanical load bearing changes when one changes the chain length. This is still work under progress. So we have taken the first steps toward designing those proteins. So in terms of length, in terms of what the end units are, in terms of how the interactions are. So the thing that we can vary experimentally, we can vary the dissociation constant between the end units. So that's by choice of what is being put, what protein is being put into the end. Now the data that I showed, it's CBM, but there is also crystalline, there is bycatcher, there is a number of other proteins that can be attached to same intrinsically disordered sequences. One can vary also the middle sequence that affects the middle part dissociation. One can do also phosphorylation to the proteins, which also changes the adhesion. These proteins are biosynthetically in microorganisms produced, and current status here is that we have the mechanism of the LLPS for the one silk-like protein and its fiber formation mechanism. We know what is happening as a function of middle block length on the condensate. We are working towards what is happening with the KDs. And the key to getting there is that we can really do the coarse-grained modeling in conjunction with the atomistic modeling, because this one allows varying the interactions between the beads and simplified systems there. Okay, conclusions. Via molecular modeling, we get synthetic silk-like protein fibers forming via hierarchical load-bearing mechanism, and it's the stronger terminal units and weaker middle region stickers. It opens in a sticker-like way when it's forming fibers. This bicontinuous network, it's possibly the reason why one can get those fibers. This indication of the zipper-like unfolding would indicate that way. And we are working towards guidelines for the tripole protein design for self-organizing materials. And in this, the interactions between the proteins segments are really a key. This is really like, I like to say that these are Lego block proteins. So one can select the blocks and work with them. It's really nice constructs. Okay, then that's like the conclusion of my talk. Before I end, I would like to advertise that we have right now in Helsinki open positions, and they are actually related to this topic. So if someone in the audience finds the topics interesting, there is experimental PhD student position within this silk-like protein things, and it's biophysical characterization of molecular assembly of these silk proteins, especially analytical ultracentrifugation. And for that one, you should contact Markus Linder. You can also contact me. I would be happy to forward applications to Markus. Also, it's possible to work together in computational and experimental things in this, because these are positions funded by Academy of Finland Center of Excellence in Life-Inspired Hybrid Materials. So these are joint funding positions between the groups. I'm looking for postdoc modeling active soft materials, including these silk proteins, also some other soft materials and polymer materials, essentially from molecular to materials level. And also for postdoc, it's possible to combine experimental work there. Okay, people that I should thank. My own group, the people who really did the simulations in this one, Alberto Scacchi, my postdoc, he's in charge of the coarse grain simulations. Mikko Niemistö, whose picture is not here, helped Alberto. And then the atomistic detail work is by Dr. Piotr Patus, who is my former postdoc now in Krakow, Poland. So he's to thank for all those atomistic detail simulations. Of course, everyone else in the group as well. The experimental collaborators, they are Markus Linder and then Jaakko Timonen. I did not now show Jaakko's work, but he's also very important in this condensate studies of the active materials. Funding, dominantly Academy of Finland, some other funding sources as well. Okay, that's all. I suppose I'm almost in time. Thank you very much.
Yeah, thank you very much, Maria. It's wonderful, and
maybe I'm putting back the recruitment slide.
Yeah, good.
Are there any questions?
And it seems huge work for me, because very big systems and very complicated molecules.
Yep.
So if I look at this LLPS as a phenomenon, so can one simplify it and say that basically operating close to the theta point, so you are either having extended structures or condensed structures?
It's like a coexistence of two free energy minima. So, so the dilute phase is extremely close to the condensate phase in free energy. So the system splits into two states.
And
does that answer your question?
Well, more or less.
Yep.
And so if I look at it, so the intrinsically disordered regions are, I suppose, quite critical for, especially in this kind of case, because then you have this possibility to separate. So now, what do you think are the driving forces? Because there's, of course, we have hydrogen bonding in these systems, there's electrostatics, but the coarse grain model itself didn't seem to have electrostatics, but it seems to be more driven by hydrophobicity.
The coarse grain, it just has the Lennard-Jones. So the Lennard-Jones captures effectively the electrostatics, hydrophobicity. It's all lumped into that single Lennard-Jones attraction. At atomistic scale, it's charge-charge, so point-like charge-charge interactions. So if there is a positive amino acid, negative amino acid, those attract one another. Then additionally, there is pi-pi connections. So if there are rings, and then pi-cation interactions at molecular level. So, pi ring and then cationic amino acid group. Then additionally, alpha helices, they are hydrophobic. So then it's hydrophobicity, and beta sheets are also hydrophobic.
If I may continue for one more on this. So these are basically homotypic systems, right? So you have one type. What would happen, because just what you described is kind of complex system, if I have heterotypic system, does it still occur?
So the question is that if this is simple conservation versus complex conservation. In principle, it works the same way for complex conservation, but then you have a negatively charged polymer and a positively charged polymer, and they complex. And actually, we have been working quite a lot on polyelectrolytes and polyelectrolyte complex conservation. The conservate phase there, it's very closely related to the protein condensate phase. So these are simple conservates or simple condensates. There is just one species forming the condensate. I would like to say that it works the same way, but there is the thing that there are two oppositely charged species in a complex conservating system, so it complicates things a little bit. I am not that far yet that I could say that whether, like, what are really the similarities, what are the, but I would very much like to go there. And like a large part of our research is those complex conservates. So we are working on it also from that side.
Thank you.
Yeah.
Okay, thank you. Any questions from here? But I have a question about coarse-grained simulation. It's known typically that Brownian dynamic simulation doesn't take into account hydrodynamic interactions. Probably this is not strong influence of hydrodynamic interactions on structure of materials or structure of the system studied, but it influences sufficiently dynamical properties, really. Do you deal somehow with hydrodynamic interactions, or do you avoid it for some reason?
So right now the Brownian dynamics doesn't account for the hydrodynamics. We have some dissipative particle dynamics which takes into account the hydrodynamics, but for that one the time scale is not enough. So we tried that and we couldn't get it to equilibrate for these silk structures. So right now the modeling results don't capture the hydrodynamics. And I have not yet assessed how much it affects on the diffusion coefficients because we are matching with the diffusion coefficients that come experimentally. But for sure it does affect. You are very much right. Then there is another question. We have also experimental data. What happens if one puts an electric field over these, which causes electrohydrodynamic phenomena? And modeling that gets really complicated without the hydrodynamics description. I haven't started it yet. Yeah, so that's a very good point.
Yeah, okay. So, any questions? No? Maria, thank you very much for your talk. It's huge work, I believe, and very interesting. Thank you very much for participation in our conference. And so now we have coffee break till 6 p.m. and then we will return and we will continue our conference. Thank you, Maria, once again. Bye.
Yeah, thank you.
So the coffee break is over and we're going back to work and back to our talks. And the next speaker will be Dmitry Tolmachov from the laboratory, Mega Grant Laboratory, headed by Mikka Kartunen here. And he will talk about atomistic simulation of polyelectrolytes.
Thank you very much, Sergey.
Of biological polyelectrolytes, as I see. Yeah? So, Dmitry.
Thank you very much. So, indeed, I want to talk about atomistic simulation of polyelectrolytes in salt solutions, and this topic is very close to the topic of presentation of Gekter, who talked about it yesterday. And moreover, he is one of the co-authors of some of these works. So, first of all, I want to talk about motivation of our work, and it's related to ability of polyelectrolytes to chelate mineral ions. And this is very important for number of the systems that can be investigated. It's like biological systems, development of corrosion inhibitors, development of clean and drainage systems, and filters for water purifications. And our motivation firstly was understanding of molecular mechanism of synthesis of organomineral composites for bony plants. Basically, bone is composite material which consists from collagen and mineral phase, mostly calcium phosphates. And mineralization of collagen goes by special peptides which plays role of delivery vectors of mineral phase to the volume of organic matrix. And recently, 10 or 15 years ago, experimental colleagues started to use such called biomimetic approach, where they used polyelectrolytes for such mineralization, and they saw that without polyelectrolytes, collagen matrix mineralized only on the surface, but if we use polyelectrolytes, mineralization occurs in volume of the organic matrix. So we investigated two polyelectrolytes. It's polyamino acids, polyaspartic acid, and polyglutamic acid. It's important to note that usually experiments used polyaspartic acid as a deliver vector in synthesis of organomineral composite materials, and their chemical structures is very similar. Only the length of side chains is different. So, despite the similarity in chemical structure, the interactions with ions and influence on mineralization, formation of mineral phase, is different. First of all, it is known from the experiments that glutamic acid does not yield mineralization of collagen sponge as do aspartic acid. And second of all, it's known that there is different effect on calcium carbonate crystallization, and aspartic acid is more inhibitor, if I can say that, for crystallization process than glutamic acid. So to understand the nature of these experimental results, we performed molecular dynamic simulations. And when we talk about molecular dynamic simulation of polyelectrolytes, it is important to know the challenges that we face. And first challenge was well described by Gekter yesterday, but I want to talk about it a little bit more. So the parameterization of ion-ion interaction is in charged fixed force fields, and absence of polarization effects causes ion overbinding on polyelectrolyte. So to solve this problem, one can use, of course, polarizable force fields with direct account of polarization effect, but it requires, it has very high computational cost, and this high computational cost gives some limits to available time simulation, which of course in some cases is very important. So it's preferable in some cases to use correction to charge fixed force fields, such as NB-fix, which based on artificial increase of contact distance between charged atoms. Or electronic continuum corrections, which was described yesterday by Hector, and it's based on mean field approach and charge scaling. So in our simulation, we considered 48 systems. We checked 2 polyamine acids, as I said, 2 types of counterions, sodium and potassium. From experiment, it's known that it's relatively low concentration of salt. The effect of sodium chloride and potassium chloride on these polyamine acids should be the same. We checked 7 force fields, 2 corrections of them in some cases, and each simulation was performed during 1 microseconds. It is important to know that some of the results was published in our recent paper in Journal of Chemical Theory and Computational, and this paper found very good response from scientific community and have a good number of citations. So let's move to the results. First of all, I want to discuss effect of radius on radius gyration of ion overbinding. It could be seen here all values of radius gyration for all systems are presented. Red line, it is results for systems with potassium, sodium, it is black line. It can be seen that in some cases the difference between values of radius gyration is very big if we change potassium on sodium. So this is these systems. What's the reason of such behavior? It is overbinding, as I said before. This overbinding leads to formation of sodium bridges between charged carboxyl groups. You can see by pink line that amount of such bridges is very high in the cases where difference of radius gyration between 2 different systems is high. Interesting that electronic continuum corrections in some cases doesn't solve this problem, and we think that it is due to the fact that decrease of charge on carboxyl groups, we decrease also repulsion between them, and it is artificially changes value of radius gyration of the chain, and effectively increase the density of the charge of the chain as whole, and this leads to additional adsorption of sodium. So this is an example of ion bridge, classical example of some artificial results, and as you can see, this bridge can consist from several different carboxyl groups and several ions. So this is about structure, and also it is important to know that this artificial sodium bridges affects dynamic properties of the system. Here we can see first graph is show distance between the ends of the chain, and it's relaxation time of distance between the chains of the chain. And we can see that sodium bridge leads the increase of time relaxation, even sometimes in several magnitudes. While in system without sodium bridges, relaxation time is more or less the same. Here the systems with the calcium bridges. Also we checked relaxation time of dihedral angel backbone of the chain, and it is interesting that in this case the effect of sodium bridges is more unpredictable. Of course, in most cases, sodium bridge system with natrium, sodium has more relaxation time because of the sodium bridge. But in case of, for example, charm 36, the relaxation time of this angel is higher in case of potassium ions. So when you have overbinding in your system, the results could be unpredictable when we are talking about local change of local structure of the chain. And due to the fact that we simulated a lot of force fields, and the most obvious question, which force field is better? And we tried to check it. We compared our results to existing experimental results, which show population of different conformations of the charged polyaspartic and polyglutamic acids. And we obtained for each system, we obtained plotted Ramachandran plots and divided it on different populations which related to different conformations and compared it with the experiment. It is the green part of the table. It is part which are close to experimental values, and it can be seen that there is no force field that perfectly describes the experiment. But the most close is charm 26. That is interesting result because it's quite old force field, and they are rather better force fields. But anyway, it gives the most close result to experiment. But we can see that fraction of alpha helical conformations here is higher than it should be, and it's a very known, good known problem of charm 27, and more new force fields, charm 36. Developers try to evolve this problem, to solve this problem, and you can see that number of alpha helical structures is much lower in case of charm 36. But anyway, they solved this problem, but the population of another conformations was changed too. So at this time, for these systems, charm 27 looks like most appropriate force field to simulate, to use. So we use this force field in our next simulation of polyamino acids with calcium chloride solution in different concentrations. And first of all, we checked and we tried to investigate how calcium chloride affects on dynamic of the chain. And here you can see the transition frequencies between different states on Ramachandran plots. You can see that addition of calcium chloride solution leads to decrease of the frequencies. In some cases, the transition between main regions on Ramachandran plot mostly forbidden in case of solution of calcium chloride. And of course, the reason of such behavior is calcium bridges between carboxyl groups, which stops these transitions. And this is quite a problem because these strong interactions causes a problem with sampling in our simulations. So to resolve this problem, there is several methodics such as metadynamic, replica exchange, or Gamiltonian replica exchange. And I want to talk about them a little bit more. So metadynamics is a very powerful tool, and it's based on scan of an energy landscape with addition of the potential which is dependent on the collective variable. And the problem is in every system to find this collective variable that will increase our sampling and will guarantee to us full statistical obtaining of full statistical ensemble. And in case of some polyelectrolytes and ions, the most appropriate, I think, collective variable is the distance between ions and carboxyl groups. But in our case, the number of charge groups and ions is very high, and the number of distances is much higher, and it's totally impossible to use these collective variables. So it is one can use, for example, a number of ions adsorbed on charge groups as collective variable. But again, it's not guaranteed that you will obtain full statistical ensemble in this case. So another method is very common and very powerful. It's replica exchange. When you simulate with different replicas in parallel, and these replicas can exchange states between them. But in case of simulation of polyelectrolytes and calcium and mineral ions, the problem is that calcium bridges has entropic nature, and the increase in temperature does not lead to its destruction, and so in higher temperatures the problem is of sampling there too, so we cannot use this method. And so last method that we used here is Hamiltonian replica exchange. The same, we model in parallel several replicas, which are different in series of Hamiltonians, and in our case there was work Lemke et al. Who suggested to use 3 Hamiltonians. It is Lennard-Jones potential between calcium and carboxyl groups. In higher replicas, we artificially increase distance between calcium and carboxyl groups. Then in higher replicas, we change potential of Degenerate angel, make it more flexible. And also we increase the temperature to increase diffusion of water and calcium to obtain faster new states of the system. So this Hamiltonians allows and ensures generation of new states in higher replicas. And second thing that we have to ensure the exchange states between these replicas. And to make it, we have to choose replicas with close energy between them, because it's one of the parameters that determines exchange between states. And in this work, there was 8 replicas, simulation of 8 replicas. But anyway, it was oligomer. In our case, we obtained exchange between replicas using 21 replicas. We think it's because polymer regime, it has a lot of calcium bridges, and the restrictions in this case much higher. So here we can see radius of gyration, or distribution of radius of gyration for every replica in one of the simulations. You can see that there is new states appears in each replica, and higher replicas the radius of gyration can can have a very wide distribution. So we have new states, and we have exchange between different replicas of the stage. So our method is working. So let's go to the results. And first of all, we had to choose the systems for the simulation, and we chose 2 concentration. First of all, minimum of radius gyration for aspartic and glutamic acid, and second of all, concentration when the difference of aspartic and glutamic acid appears. Here we can see distribution of radius gyration. And we can see that there is a big difference between aspartic and glutamic acids. You can see that at higher concentrations of salt, the polyglutamic acid is collapsed while aspartic acid is elongated and the distribution of this chain is much wider. The reason of such behavior, we believe, lies in length of the chain, because it's only chemical difference in our polyamine acids. The idea is that adsorbed calcium ion adsorbed on carboxyl groups interact with each other and push away a little bit each other. And to maximize the number of adsorbed ions, chain has to be elongated. But in case of glutamic acid, the longer side chains allow to distribute calcium, adsorbed calcium ions, and to save collapsed backbone. So this is the reason of such behavior. And we think that this results explains the experimental results that I mentioned at the beginning of my work, beginning of my talk. Polyaspartic acid, it is known, can form polyinduced liquid precursor. It's like liquid-like droplet that can easily be involved in organic matrix by osmotic pressure and induce mineralization in it. But if we don't use any polyelectrolyte, mineral phase is more solid and cannot go to organic matrix, and only surface is mineralized in this case. In case of glutamic acid, the situation is very similar, because collapsed chain of glutamic acid cannot form such liquid-like precursor, and droplets are more solid and again cannot be penetrated to organic matrix. So it is important to know that we performed some additional simulations with different salts. It's mainly calcium phosphate salts, and we obtained similar results, which show that in case of aspartic acid, the organomineral complex is more flexible than in case of glutamic acid. So this is all for now, and I'm ready to answer your questions. Thank you very much.
Okay, thank you, Dmitry. Any questions from here? And questions from Zoom? Yes, Alexei.
Thank you very much for the talk. So impressive is the first part of your work, where you probed a different force field to find the optimal one. So you have demonstrated that the best one is CHAM 27. It's good, except one point concerning related to the degree of heat. But CHAM 36 is good for. What is your opinion? What is your opinion? Is it possible to improve somehow CHAM 27 to make it proper working for this missing point?
Okay, thank you for your questions. Of course, I think it is impossible, but the question is, should we do it or not? Because I think force field should be general a little bit. So the CHAM 36 was not parameterized especially for these polyamine acids. They had a lot of experimental and computational work to parameterize parameters for peptide simulations and in different situations. So, for my opinion, now it's not very surprising that we obtain these results. But anyway, of course, we can try to change parameters to increase the results of CHAM27, for example. But these parameters will be, you can use it only for these systems, and they will not be so general. So, for my opinion, you should know, it is important to know where you lie, where simulation lies, and which problems it has. And this knowledge will give the better understanding of the results and will help to understand if you get artificial results or not.
Thanks.
I have also one question. Also in the first part of your work, you talk about overbinding of counter ions, and it is well known that big ions would absorb more polyelectrolyte than required in electrolysis. So it's possible to observe some overcharging effects in real systems when big macro ions, so-called macro ions, absorb polyelectrolytes. In your case, overbinding is for small sodium ions, and in this case, what is the driving force of this overbinding? I think it's unphysical, yeah, probably, because it's too small. But in some force fields, it's still there is absorbed. What is the driving force of overbinding in these force fields?
For my opinion, of course, driving force is electrostatic interactions. It's no question. But we observe this quantitative results, difference in quantitative results, due to parameterization of force field and parameterization parameters of interaction chain as whole, dihedral angles, bonds, and so on. So it's somehow, I think the overbinding with sodium between overbinding could be appeared in, for example, force fields that does not give us the problem with radius gyration, but the interaction in force field such that in this force field, this overbinding causes problem even in conformation of chain. It is important to know that there is no salt, it's just counterions, and when you simulate polyelectrolytes, you should use counterions. And before, recently, like 5 years ago, or maybe 7 years ago, people just used some counterions, for example, sodium, and didn't think that this sodium can influence the chain conformation. And in some cases, it does, and it is very bad. But it does not mean that there is no overbinding in other systems.
But am I right that if we talk about electrostatics, that means that these force fields, where we see these sodium bridges, partial charges for carboxylic groups is wrong, correct? Or it's a complex system?
I think it's a complex system. I think the problem is absence of polarization effect in these force fields, and as it is very related to this question is very related to the talk of Gector's talks, because we don't have polarization effect. There is overbinding, and we have to take to account this polarization effect to be sure that we will obtain correct results. So the idea is that the problem mostly in polarization, absence of polarization effects, but not in charge value as it is.
Okay, Thank you very much. If you have no questions from
I have a question.
Zoom, yeah,
Wait a
Mika.
Yeah. So, what's your opinion? So, now here we have the problem with electrostatic interactions and the ions, but then many of the problems seem to be with amber when it's combined with corrections, and also without corrections. So, what do you think? How big a problem are the chain parameters?
It's a very good question. It's a very good question, and I can talk only about these polyamine acids, and that the things that we saw that there's quite a big problem in, for example, Ramachandran plots obtained by amber phosphiles, because I think it's because different approach to parameterization to reproduce these dihedral angles. If we take CHAM36, they use CMAP to reproduce Ramachandran plot, and for me it is more convenient and right way to obtain better results. Maybe the absence of these potentials is the key problem of amber phosphiles for reproducing for simulation these molecules. But again, when we'll talk about some more complex peptides, the picture could be very different.
Thank you.
Okay, so thank you, Dmitry, once again for your talk. And Dmitry finished our simulation part of our conference and our meeting. And the next talk will be given by Professor Tatiana Buttova from France, from Mainz Paris-Tech. Tatiana, oh, hello.
Yes, I'm here. Hello, hello. Can I should share the screen. Can I do this?
Yeah, you can do.
Okay. Do you see my screen?
Yeah, it's starting.
It's starting. Good.
Yeah, great. We see it. And the talk.
Okay.
Yeah, the talk will about extremely new materials, bioaerogels.
Yes, thank you very much. Hello, everybody, and my dear colleagues. Добрый вечер всем. Okay, so today I will make an overview. I'm sorry, there will be no simulation at all. It's pure experimental work. And as these bioaerogels are new materials, I will not focus on one only property. I will give you an overview, and we will start with the introduction about aerogels in general. Then we will move I will explain how to make bioaerogels, what are the main characteristics, then some examples of properties, and then I will try to list the open questions and prospects. So what are aerogels? I will just try to decrease this. Okay. So what are the aerogels? In fact, aerogels are very old materials. They were discovered in the 30s of the past century by American scientists. Aerogels, they are solid open pores networks with very low density. So you see the values here around 0.01 to 0.2 gram per cubic centimeters. They are highly nanostructured materials, which means that they have very small pores in the mesopores size, which means from 2 to 50 nanometers, and small macropores below 100 nanometers. And due to this nanostructuration and very low density, high porosity, these materials, they have very high specific surface area. The specific surface area is the sum of the areas of all internal pores. So it can go up to and even above 1,000 square meters per gram. This is huge. And these images are showing different types of aerogels that are known in literature. So the first ones that were synthesized, they were silica aerogels, and these are the two upper images of scanning electron micrographs, scanning electron microscope. Then at the end of the past century, synthetic polymer gels were synthesized based on resorcinol formaldehyde, on polyurea, and these are the two other images. And then at the beginning of the 21st century, with the increased interest to bio-based materials, aerogels were synthesized, or they were prepared. In fact, there is no synthesis per se, were made based on polysaccharides. Here I'm showing the images of alginate aerogels and a couple of cellulose-based aerogels. So what are the applications of aerogels? The only one application that is really more or less developed at the pre-industrial scale, that's for silica aerogels, and this is for thermal insulation, because as I will show you, silica aerogels are thermal superinsulating materials. Then it is possible to do pyrolysis, for example, of polymer-based, synthetic polymer-based aerogels, and then there will be carbons with high specific surface area that are interesting to use in batteries or fuel cell membranes, also as a catalyst and catalyst supports for absorption, and purification. So this being said, as a short introduction on aerogels, how to make bio-based, how to make bio-aerogels. So if you want in general, just a brief reminder, if you want to make a dry porous material, here we are not touching membranes, dry porous material from a gel or from a solution. Here is the classical pressure temperature diagram with a triple point. If you dry your wet material directly by simple evaporative drying, there is a capillary pressure that is developed, and this is a schematic presentation of the pore, with the material of the pore and the liquid which is inside. So when liquid is evaporating, there is the surface tension which is created between the liquid and the gas. Then there is a contact angle, meniscus, that is formed in the pore, and also the capillary pressure depends on the pore radius. So smaller are the pores, clearly the higher will be the capillary pressure. Also, it depends on the surface tension on the liquid and the gas. So if we want to make a porous, nanostructured materials, clearly we have to avoid this capillary pressure. And there are two ways to do it: to do freeze drying or lyophilization, where you are freezing the liquid in the pores and then sublimating it. Usually it is done with water. Or it is possible to do drying in supercritical conditions, where you are increasing pressure and temperature above the critical point. And in this critical state, supercritical state, the substance is neither liquid nor gas. It is very diffusive. The densities between the liquid and the gas. And the main thing is that there is no surface tension between the liquid and the gas. So theoretically, in this case, the capillary pressure is zero. So again, if you want to avoid the collapse of the pores due to capillary pressure, the way to do it is to use drying in supercritical conditions. It is possible to do freeze drying, but usually if it is done from water, the ice crystals that are growing inside, they are completely modifying the morphology of the gel, of the solution. So the final material can be porous, but it will not reflect the morphology of the starting gel or solution, and it will not be, usually it will not be nanostructured. So the classical pathway to prepare aerogels is to start with a solution or colloidal dispersion of small entities and something. Then with a chemical reaction, there will be a soil that will be formed, then a gel, and then with supercritical drying, aerogel will be formed. Now, for bio-based aerogels, there is no need. It is not that there is no need. There is no this step. There are no small molecules, as it is in the case of silica or synthetic polymer aerogels, because for silica and synthetic polymer, you start with the monomers. For bio aerogels, you start with the polymers that are made by nature. For example, from polysaccharides. So you are making a polymer solution. You can gel your solution or not. And then as far as the solvent of polysaccharides, let's say, or many bio-based polymers, is aqueous media, and water is not miscible with CO2, it is necessary to do the solvent exchange, which means you have to replace water by a solvent which will be miscible both with water and with CO2, and usually it is acetone or ethanol. It has to be said that acetone or ethanol, they are not solvents for the majority, or at least for native polysaccharides. So here, as a precursor, we don't have a gel, but we have a sort of a wet network of coagulated polymer. But the magic point of polysaccharides is that the polymer is not completely collapsing as many synthetic polymers. It is keeping the 3D structure, so it keeps the network morphology. It can shrink a bit, more or less, but it still keeps a 3D dimension. Another option is to use nanocellulose or nanochitin. In this case, it is a dispersion. Usually, again, it is dispersion in water. Needed water has to be exchanged by ethanol or acetone to be able then to use supercritical CO2 and then to make a bioaerogel. So the advantage of bioaerogels is that there is no need in polymerization. As I said, there is, in fact, we cannot say it is a synthesis, it is a preparation. There is no chemistry, absolutely no chemistry here, no cross-linking. At maximum, to make a gel, you can add, for example, for alginate or pectin, let's say calcium ions. But there is a need in solvent exchange. And obviously, there is a need to very well master the properties of the starting polymers, because polysaccharides are very different. And what I will show today is that we will use biopolymer solution, polysaccharide solution. I will not speak about nanocellulose. We did not do any work on nanocellulose. I know literature, so if you have questions, I may be able a bit to reply to your questions. So what are the main characteristics of bioaerogels? The first thing when you have a porous material is to measure the density. So this is an example of the density of cellulose aerogels. And this is the collection of data from literature. Cellulose was dissolved in different solvents. Then different non-solvents were used, acetone, ethanol, and some others. The cellulose of different molecular weights. So everything is combined here. And you see, okay, the density is low, but the density varies depending on the preparation conditions. We will not go into details to this. What is important is that there is this straight line which shows the case of no volume change during all the preparation steps. And all the data for density are above this straight line, which means that our sample undergoes volume contraction during all the processing steps, which is good, easy to predict, because when you are putting a polymer which was dissolved in a non-solvent, there will be a certain contraction, and then CO2 also is non-solvent for cellulose. What is interesting also, as I mentioned, that the properties of the starting polysaccharide has to be well understood. And here is the example of the density of pectin aerogels as a function of the pH of the initial solution. And you see the density is very low, all data below 0.15 gram per cubic centimeter, but it varies a lot. 3 times you can vary the density depending if the starting solution is gelling or not. This is marked with G, with gels. So these are the gels that were then put in non-solvent and dried. And these are the solutions. So there was no gelation here. And you see that the sample is contracting, and that is why the density can vary a lot. So the message to take is that there is a shrinkage or contraction at each step of the preparation, and there is a strong influence of the strength, sort of a strength of the network before making the solvent exchange and before drying. Now the morphology is certainly very interesting for porous materials, and here is an example for cellulose aerogels. Cellulose was dissolved in two different solvents, in sodium hydroxide, where cellulose was gelling, and in ionic liquids, where cellulose is not gelling. And you see there is a difference in morphology. And in all cases, there is a rather high specific surface area of several hundreds of square meters per gram. For starch aerogels, the morphology depends a lot on the type of starch, or better to say, on the ratio of amylose to amylopectin in the starch. So you see for waxy potato or waxy maize, where there is no amylose, there are large pores, and the specific surface area here is low. Then when you increase the amount of amylose, which is a linear polymer and has a special kinetics of retrogradation, so there is an interplay of when amylose, amylopectin is gelling with different kinetics and so on. But you see that the morphology is very different with fine network when there is a certain amount, let's say, of amylose, also with a rather high specific surface area. And probably the most beautiful case is pectin aerogels. Here are the examples when pectin, here the starting is a solution without any cross-linking. And here are the two examples when pectin was cross-linked with calcium a little bit and more. So the network was formed, and with a very fine network structure. And if looking at the specific surface area for pectin aerogels, here specific surface area is plotted again as a function of the pH of the starting solution. So if pH of pectin is very low, it is gel that is formed. Then here are two cases shown for when pectin was cross-linked with calcium and not cross-linked with calcium. So when pectin is cross-linked with calcium, it is gelling, and the pores, the gel is contracting less, but the pores are larger when pectin was not cross-linked at all. So so you can tune the morphology and the specific surface area by changing the starting conditions of your solution, and it can vary a lot. Still, specific surface area is very high, from 300 to almost 600 square meter per gram, but okay, you can play with this depending on the application you want to use for your bioaerogels. So these were the main characteristics, and then few examples of the properties. And as I mentioned, the silica aerogels, it is a thermal superinsulating material. What it means that the thermal conductivity of silica aerogels is lower than the conductivity of the air. So you have, it is a bit magic that you have a matter that you hold in your hands, a porous material, which has a thermal conductivity lower than the surrounding air, with this material having air inside the pores. And this is due to physical effects. So in total, the thermal conductivity is the sum of the conduction of the solid, of the skeleton. So if you want to decrease thermal conductivity, you have to decrease the density. And then also the conductivity of the gas. And there is a Knudsen effect, which is saying that if the pore size is lower than the mean free path of the molecule, okay, here air molecule, so then the conductivity of this gas in the confined pore will be lower than the conductivity of the gas of the ambient air. And then radiation conduction is low in this case. So we obviously, okay, that this is a hot topic, thermal insulation, because everybody wants to save energy and to decrease the thermal conductivity. So we did a lot of work trying to decrease, okay, first to explore and to decrease the thermal conductivity of our bioaerogels. And for example, for P-starch aerogels, we got thermal superinsulating materials from a certain type of starch where we have a very fine network. But for example, for cellulose aerogel, we did a lot of work, and we didn't manage to have thermal conductivity below that of the air. Either pore walls are too thick or pore size are too large. Whatever you do, and to my knowledge, nobody managed. It was possible to make thermal superinsulating cellulose aerogels from nanocellulose, but not when cellulose is dissolved. And again, the most beautiful example is for pectin aerogels with very fine network. And you see the conductivity of the air is marked here, 0.025 watt per meter per Kelvin, and all data are below. And it is making a classical U-shaped curve of the conductivity as a function of density. Another example is that you can do pyrolysis of your bioaerogel and get carbon with high specific surface area. It was tested for electrochemical applications. A small battery was made with our carbons, and it has very nice, it has better discharge properties than the reference material of the company with which we worked. And the final property is that it is possible to use bioaerogels for biomedical applications, because that's pure polysaccharides, no toxic, nothing toxic. And the advantage is that they are lightweight, they are dry, so there is no bacterial growth. Preserves the shape and possible to make large variety of materials and so on. And it is possible to put some drug, some substance inside, either so at different steps. And then this drug will be released in different ways, depending if your matrix, your aerogel is soluble in the conditions or not. So this is just an example that, again, with pectin aerogels, you can vary the starting conditions, you can vary network morphology, you can then vary the density, and then here is plotted the theophylline release as a function of time, and it is different depending on aerogel properties and all the solubility kinetics of the dissolution of the matrix. I think I'm running out of time, and I will finish with the conclusions, and then we will go to the open questions. So bioaerogels are zero toxicity, nanostructured polysaccharide networks with very low density, tunable morphology, and high specific surface area. So there is a need to know the properties of the starting polymer and of the state of the matter, gel or solution of the precursor, with numerous applications in life science, in engineering, and electrochemical. And there are a lot of open questions. These are the new materials. So, okay, we need to understand how chains are packing during solvent exchange, when we are changing solvent to non-solvent. The influence of chain rigidity, the influence of hydrogen bonding, the presence of charges or not. And I should say that modeling is non-existent for bioaerogels. Then the funny point is to understand why cellulose aerogel is not thermal superinsulating materials, but this is a question related to the first one. Then the question is how to avoid supercritical drying, if it is possible to do, because it is expensive, it is high pressure technology. For applications would be good to avoid. How to avoid the closing of the pores. How to avoid aging, because polysaccharides are absorbing humidity. And to develop different applications. And with this, I would like to thank all the people, that there was a huge amount of people who worked on this and are still working, and different agencies that financed our work. And thank you very much for your attention.
Okay, thank you very much for very impressive talk. I would like to start questions actually. Typically, probably it's very easy and stupid questions, but for many applications, it is required that materials have some specific mechanical properties. So could you comment on mechanical properties of these aerogels? Are they brittle?
Yeah, sure. Yeah, sure. We did it. Just I didn't show. Yes. So the bioaerogels, they have very nice mechanical properties, in the sense we did compression experiments. That's the easiest thing to do, because we were making cylinders and then compressing. So you can compress up to 80% of strain, and they were not breaking. And the compressive modulus was from few megapascal to few tens, depending on the density of aerogel. So to compare with silica aerogels are very brittle. You take them and then they're breaking in your hands. Synthetic polymer aerogels are very resistant. So bioaerogels, the elastic recovery is very small. This is very low. So they're not like foams.
Yeah, I see. So, okay, thank you. Any questions from auditory? Yes, Mika?
Yeah, they are very fascinating materials.
Yeah.
Can you comment on the thermal conductivity? So what's the temperature range where this kind of materials can operate as let's say long term?
Polysaccharides, you should not put too high temperature, they will burn. So it should not be more than 100, I would say. Like about cellulose, it's cellulose. So,
how about silica-based? One could imagine.
But silica aerogels are very resistant. It's true. Yes. Okay. Silica. Look, I don't remember by heart, but silica should be several tens. Several hundreds of degrees of Celsius.
Okay, that's fairly high.
Yeah, that's inorganic. Yes.
Thank you.
So, if no more any questions,
ask one more question.
Yeah. Okay, Mika.
Okay, so as they are not conducting materials, but how about decorating those, or somehow? Well, decorating with magnetic materials inside, so that one could guide, for example, the particles.
Yeah. It's we did it. We put it was just for fun. We put magnetic. We dispersed magnetic particles in solution, and then made aerogels, and then you have magnetic aerogel. You can put a lot of you can put a lot of things inside, and then the substance that you put inside the particles or whatever, they should not be soluble in CO2. Otherwise, you can put, the advantage also for aerogels as compared to hydrogels, that you can make interpenetrated networks. What I did not show the slide because of time. We made cellulose pectin interpenetrated aerogels. If keeping them in hydrogel state in water, pectin will dissolve. when it is aerogel, both components staying and then staying dry in the dry state, nothing is happening. So there are, I think there are much more options or possibilities of making different things, different structures, and combining different type of materials within aerogels, because in the dry state nothing then is happening. And you can put, we did organic inorganic aerogels, we did pectin silica aerogels, for example. So there are a lot of things that can be done.
So one could imagine, say, using conjugated polymers to make them conductive. I mean, it's a percolating structure, right? So
absolutely. Absolutely. This what starts to be done with nanocellulose, nanocellulose aerogels, but not much is done for when you are dissolving polysaccharides. Yeah, the only thing we are missing is funding. You know, there are a lot of ideas to test. So
very good. Thank you.
thank you.
Okay. Thank you once again. Thank you for attending our conference. And so we move further to one more experimental work made in our institute, and Ilya Averyanov will make his talk on improvement of osteoconductive properties of polyester materials. Ilya, are you here? Yeah.
Yep. Hello. Good evening. Good day. Good morning, everyone.
Yeah. We hear you and see your presentations, so the time is yours.
Yeah. So my report would be on the improvement of osteoconductive properties of polyester materials with chemically modified non-crystalline cellulose. So this is a work that is the part of a big project funded by Ministry of Education of Russia. We did it in collaboration with St. Petersburg State University and the Institute of Technical Chemistry of Hanover. So first of all, I would like to talk about the why do we do this? Because why do we want to create materials with osteoconductive properties? There is a concept of tissue engineering when we take the autogenous cells from the patient, cultivate them in vitro, then we take this newly created implant that contains of the scaffold and of the autogenous cells and implant it in a patient. Thus, we can reduce the risk of inflammation and the risk of negative immune response to this implant. Particularly, our group, we focus on the creation of materials for scaffolds for bone tissue engineering. That's why we are working within this project with the nanocrystalline cellulose as a main topic. Here this is how we see it. We would like to make a biocomposite material, make a scaffold out of it, and this is roughly the idea behind, because real bone tissue is biocomposite. It contains of cells, it contains of minerals, it consists of proteins. So what we want from a scaffold for bone tissue engineering are controllable mechanical properties, improved biointeractions, because it is well known there are a lot of polymer materials even now on the market, like polylactide, polycaprolactone, but mostly they are inert materials. And these materials, from one point of view, they are biodegradable and biocompatible, but from the other point of view, they lack hydrophilicity. And they lack the possibility of controlled interaction with cells. So the idea is if we introduce some bioligands to this scaffold, we could improve the overall result of implantation, and we could improve namely the biomineralization of the material, and thus improve the healing of the wound in bone tissue. So our idea was to take biodegradable polyester like polycaprolactone or polylactide and mix it with non-crystalline cellulose that will be modified with polyglutamic acid. As Dmitry Tolmachov told us, polyglutamic cellulose improves the absorption of calcium ions on the surface. And there are experimental works published that tell us polyglutamic acid actually improves this property of material. So we decided to take this polyglutamic acid that we synthesized in our laboratory and attach it to non-crystalline cellulose. Our idea was that non-crystalline cellulose will give some sort of reinforcement to the matrix, to the polymer matrix, and polyglutamic acid will give this biomineralization thing to the matrix due to its numerous carboxylic side chain groups. So what we did, we oxidized non-crystalline cellulose with sodium periodate, and then used the newly formed aldehyde groups to attach low molecular weight, about 2,000 molecular weight polyglutamic acid to these molecules. And so this molecule, we can say modified cellulose, was used for further experiments. First of all, we wanted to test what does it improve actually in mechanical properties of polyester materials. So we prepared, with the aid of our colleagues, we prepared samples of polycaprolactone mixed with neat cellulose, here and here, 5 and 10%, and mixed with polyglutamic acid modified cellulose. So we could say that these tests showed us young moduli and compressive strength here. We can say that all tested materials demonstrated plastic nature of deformation with high deformation resources. When compressed to 80%, none of the samples began to collapse. As we can see here, the introduction of neat or modified non-crystalline cellulose into polycaprolactone matrix contributed to an increase in mechanical properties. In turn, modification of non-crystalline cellulose did not lead to a noticeable change in mechanical characteristics of the material under tested conditions. The properties of mixed materials, of composite materials, at the same filler contents are almost identical, and that is a plus for us because we wanted not only to increase the mechanical properties of the material with non-crystalline cellulose, but the main aim of this work was to introduce biological functionality. So here we could say that our composites did not give a great increase in mechanical properties. However, they state almost on the same level as pure polycaprolactone. So they could be used for further experiments. Using our laboratory printer purchased from GSIM Robotics, we started to mix our materials and mix our components and to print the materials into scaffolds. The ability to support cell growth is important for scaffolds for tissue engineering. Even though polycaprolactone is a well-known biomedical material, still we needed to carry out cell viability assay for the developed scaffolds because we have introduced new components such as neat cellulose and cellulose modified with polyglutamic acid. For this purpose, polycaprolactone scaffolds here, 3D printed, were seeded with human mesenchymal stem cells and allowed to adhere for 1 day. Afterward, the cell titer blue assay was performed, and we observed that all samples, all materials which were tested with this assay showed almost equal results in terms of amount of living cells. Further, we studied our materials for osteogenic differentiation. As I told previously, the main idea was to introduce some biological functionality to our materials via incorporation of non-crystalline cellulose modified with polyglutamic acid. This functionality is presumably biomineralization. So we tried the osteogenic differentiation medium on our samples and allowed our scaffold samples that were already confluent with cells, allowed them to differentiate in this medium for 1 week. Supposedly, calcium ions would deposit more intensively on the samples which contained polyglutamic acid. And then we could visualize the results with alizarin red staining and made some EDX studies to obtain some quantitative results. So here we go. On this slide, these are the images of scaffolds after cell culture. The first top three samples, we could use them as controls for the bottom three samples. Top three samples were extracted and fixed after 2 weeks in expansion medium. Bottom three samples were extracted and fixed after 1 week in osteogenic differentiation medium after 2 weeks expansion in expansion medium. What we can see here is that the increased calcification of 3D printed materials bearing polyglutamic acid. Here it is the last column. The method of EDX analysis using energy dispersive X-ray. This method allowed us to detect calcium deposits on the surface of scaffolds after the cell cultivation and osteodifferentiation. We established that after cultivation of human mesenchymal stem cells, in growth medium, only the traces of calcium, here are the values, percentages, all the traces of calcium were detected in all kinds of tested scaffolds. The same situation observed after the osteodifferentiation of these cells in scaffolds made of pure polycaprolactone and polycaprolactone with unmodified cellulose. However, however, the evident calcium deposits after the osteodifferentiation of MSCs were detected for the polycaprolactone scaffold containing polyglutamic acid modified cellulose. In this case, the better deposition of calcium salts is explained by improved capturing of calcium ions by carboxylic groups of polyglutamic acid, which is bound to the non-crystalline cellulose incorporated in these materials. And the intensity of red staining after the alizaline red S staining also tells us the same results, that first 5 samples have traces of calcium, but the sample with the polyglutamic acid attached to non-crystalline cellulose provides the best results. So after the test with cell culture, we proceeded to the tests in vivo. With the help of our colleagues from Institute of Physiopulmonology of St. Petersburg, we performed the implantation of scaffolds in rabbit femur bones. There were 4 groups of animals and 4 groups of materials. There were pure polycaprolactone, polycaprolactone with polyglutamic acid modified non-crystalline cellulose, polycaprolactone seeded with rabbit mesenchymal stem cells, and polycaprolactone with modified polyglutamic acid modified non-crystalline cellulose seeded with rabbit mesenchymal stem cells. We could say that this sample is the most prominent for the best results, because here we see here we used as our filler as well as seeded cells on top of it prior to implantation. The defect was the defect in the bone was 5 millimeters in depth and 3 millimeters in diameter. All tested scaffolds were implanted, of course, in aseptic conditions by professional surgeon. So because we are actually chemists, so we can observe and assist, but we don't do it ourselves. After 1 and 3 months, the animals were euthanized and the implanted bone was extracted for micro-CT, microcomputed tomography study. So here we go with the images of bones on microcomputed tomography. Initially, growth of newly formed bone into scaffolds was analyzed by this method. The qualitative analysis of these images in regards of presence or absence of the bone trabeculi sprouting into the scaffold, the structurality of bone beams, the cortical closure plate, the marginal bone growths, and the bone resorption zone are summarized in here. This table. According to our analysis of microcomputed tomography images, we can conclude that after 1 and 3 months of surgery, the larger volume of mineralized bone tissue was observed in group with polyglutamic modified non-crystalline cellulose and seeded with MSCs. This one. The growth of new bone trabeculi into the scaffold, bridging of the defect area, as well as the formation of bone callus in case of this group marked green. So this growth, all these factors confirmed that it was this material was biocompatible and had at least some osteogenic nature. In other groups, the difference that we observed for the bones removed within 1 month after surgery, while the overall score for scaffolds implanted during 3 months was the same. It must be noted that new bone mass generated by scaffolds was more pronounced both after 1 and 3 months in the case of this last group, marked green. So we could conclude that our material, our biocomposite material, seeded with rabbit mesenchymal stem cells, actually improves the bone healing process, at least in rabbits. So for the same animals, we also studied the histology of the samples removed from the bones, but they are now, well, in process of, they are not yet very much analyzed and not yet ready to present. But previously we made an experiment that is that in its conclusions is very much alike with the experiment with rabbits. Previously, we made thin films of polycarpolactone and polylactic and filled them with meat cellulose and cellulose modified with polyglutamic acid. These films were implanted under the skin of rats, and rats were euthanized, and the samples were analyzed after 1 month. Overall samples, we can see that the inflammation and the amount of cells like lymphocytes or neutrophils that actually tell us whether there is an inflammation here in the studying region, in the region that we study. We can see that the materials that contained, the materials which contained polyglutamic modified non-crystalline cellulose, this inflammation is much lower if we compare it with materials with neat non-crystalline cellulose or just simple polyester. It was summarized like this. If we take our non-crystalline cellulose and use it as a filler, it gives much less inflammation. So that is both these aspects, like reduced inflammation and improved biomineralization, give us the possibility to conclude that such composite materials could be efficient in bone tissue engineering. So basically that is all that I wanted to say. Thank you for your time, and I would like to hear your questions.
Okay, thank you, Ilya. Any questions? Yes, Mikhail.
Yeah, thank you for interesting talk. I want to ask maybe you can explain more what is the actual influence of nanocellulose in these composites. So if you exclude nanocellulose and try to mix polycaprolactone with your polypeptide, maybe you will have the same results.
Yeah, thank you for your question. That is well noted point, because actually with the commercially available materials, this design is well known. When we just take some polymer and fill it with some some smaller molecule that should make some biological effect, and then it can be removed by the blood flow or by the surrounding cells. In this point, with this material, non-crystalline cellulose allows us to keep the polyglutamic acid here in the zone of the implantation, because polyglutamic acid is covalently bound to the cellulose. It doesn't go anywhere in the organism. So when the bone is reconstructed, the cellulose stays there on the place, and the effect of diminishing the concentration of this of polyglutamic acid is not observed, because it doesn't go away, because it is covalently bound to the cellulose and it sits on the scaffold. And even in the process, when the polyester polycaprolactone is degraded by the organism, the cellulose still stays and the polyglutamic acid stays there. So the bone presumably builds around it.
Yeah.
Okay. Any more questions? Yes, Dmitry.
I have one maybe silly question. You have a quite complex material which has you want to make this material, have to modify cellulose, make this material as whole, and 3D print it. So, what do you think? Is it possible to make some technology to next step of the technology to make it commercial use, or this is very complex for it? Is it possible to make it commercial?
Well, if I may, I am not a businessman, unfortunately, maybe, but still, I think it is possible. It has some, of course, some technology installment in it, because globally we need to cooperate with computer tomography, we need to cooperate with surgeons, and we need sterile conditions for the 3D printing. So in ideal world, it should be put in some big campus or in some facility that is in somewhere in one place, because now we have one institute in 2 buildings, and our colleagues are in another part of the city, and our other colleagues are in Germany. So basically, as a technology, I think it is possible. There is no rocket science in it, I think. Just the problem is to combine all the technologies together, because all of them are expensive and all of them should be operated by qualified personnel. I don't know if I tried to answer as well as I could.
Okay, I have another question.
Yes, Mikko.
Could you take the scoring matrix again? I think it was slide 11 or 10.
This one?
One after, I think.
After this one?
This one, yes, yeah. Mm-hmm. So can you comment on the other bone resorption zone? They all except one case, the PCL and NCC, have 0, 0.
That is not that's not actually a very understandable phenomena, because in my opinion, in these experiments we have a little flaw in design, because we have not so many samples, not so many specimens. It is one point of view. The other point of view is that nanocrystalline cellulose that has not been modified is actually less biocompatible, if I would say, if we look on our results with rats, the materials containing nanocrystalline cellulose that was not modified induced much more inflammation, and the size of the what it is called, the size of the capsule around the material when it was injected under the skin, it was greater in the material with non-modified cellulose. So I could presume that with this non-modified cellulose, some process, because it has, in the first stage, it has high rates of inflammation, maybe some processes were still active there, and well, the bone started to resolve, the resorption of the bone started, yeah.
Okay, thank you.
Okay, thank you. And if no more questions, I would like to thank Ilya once again. And
thank you for your time. And
yeah, thank you.
It was nice.
And
it was a pleasure to talking. Yeah.
Great. And it seems this was the last talk in our conference program. So I would like to thank all participants, all who participate as how to say, as listeners, as spectators in YouTube and Zoom. And for us, it was very important conference and very important meeting, because we have no conferences and such kind of meetings for a long time. Actually, prior this pandemic time. And thank you for organizers. Thank you for those who help us to hold it here in River Hotel. And maybe some concluding words, Mika. No. So
okay, I can say something.
Yeah.
Yeah. But yeah. So basically, repeating what you just said. So thank you, everyone,
yeah.
And especially the speakers. I personally enjoyed very much all the talks. I think talks were really good and inspiring. And thank you all the audience. Well, both there in St. Petersburg and online. And like Sergey said, there's been no conferences. The previous one in the series, like I said at the beginning, was pre-pandemic, and that was in person. And hopefully the pandemic will be gone, and we'll have the next one in person soon. So thank you very much.
Yep. So thank you, and hope to see you next time in our symposium here in St. Petersburg, next year in May. Also, I hope that we will have much better situation with pandemic. And in any case, have a good weekend or have a good Friday. And then weekend, thank you for participating, and take care of you, and see you soon again. Bye.